Finally, the last video of section 5.6 on related rates. A boy is at the top of a 15-foot ladder leaning against one wall of an alley 9 feet wide. The ladder slips, its top sliding down the wall along with the boy. Its foot sliding across the alley and striking the opposite wall at 4 feet per second. How fast is the boy falling at the instant the ladder hits the wall? Okay, so here's a little picture, not to scale, of this boy on a ladder. Not really at the top, but near the top. And the ladder is 15 feet. Now this ladder is not changing. It's always going to be 15 feet. So I don't have to use a variable for the ladder. I can call it 15. Now, it's leaning against the wall of an alley 9 feet wide. So this entire alley, and obviously you can see it's not to scale here, is 9 feet wide. That is not changing. Now, the ladder slips, its top sliding down the wall. So the top of the ladder has a certain distance from the ground. Now that's changing, okay? So let's call that y. It's a vertical distance, be a good thing to call. So the distance from the top of the ladder to the floor is y. And the foot of the ladder is sliding across the alley, so it's obviously going to be going this way, and strikes the opposite wall at 4 feet per second. So the distance that the ladder is from the bottom of the wall, we'll call that x. That is going to change also as the ladder slips. So let's list our given information. Well, we know that when the ladder strikes this opposite wall here, we know that it's going to be moving at 4 feet per second. So as the ladder slides, the bottom of the ladder is sliding in this direction, meaning x is getting bigger. So dx dt is 4 feet per second, positive 4 because it's getting bigger. Now, they want us to find out how fast is the boy falling. So in other words, how fast is the top of the ladder coming down? So that would be dy dt they want us to find. At what time? Well, we know that this rate occurs at the moment the ladder hits the wall on this side. So at the moment, the distance x would be 9. Okay, so what relationship exists between x and y here? Well, you can see we have a right triangle. So how about the Pythagorean theorem? X squared plus y squared equals 15 squared, which is 225. Now, I want to find dy dt, and I know dx dt, so these two variables are just fine. So let's differentiate. Derivative of x squared is 2x times the derivative of x with respect to t, plus derivative of y squared is 2y times the derivative of y with respect to t. The derivative of 15 squared is 0. Now, I know x and I know dx dt, and I want to find dy dt, but I don't know y. Well, at the moment x is 9, we can find out what y is at that same moment using this Pythagorean theorem here. So if x is 9, 9 squared is 81, plus y squared would be 15 squared, which is 225. That means y squared would be 144, and so y at that moment would have to be 12. So let's plug in our values into this differential equation. We have 2 times 9 times dx dt, which is 4, plus 2 times y, which is 12, times dy dt, which we're looking for, equals 0. Multiply these, I get 72. Let's subtract that to the other side. 2 times 12 is 24. That would be 24 dy dt. And then dividing by 24, I can see that dy dt is negative 3. So what does that tell us? Well, that tells us that the top of the ladder is falling at 3 feet per second, or at a rate of 3 feet per second. And there we go. One more. This last one, we have an airplane. The airplane is flying at 450 kilometers per hour at a constant altitude of 5 kilometers. It's approaching a camera mounted on the ground. So here you see a guy looking through a camera, looking at the airplane. The airplane is approaching the camera, but staying at a constant altitude of 5 kilometers. So I'm going to call this 5 kilometers because they say it is constant. I don't have to call it a variable. Now, it's approaching the camera mounted on the ground. Let theta be the angle of elevation above the ground at which the camera is pointed. So theta is this angle above the ground at which the camera is pointed. So that angle right there is theta. When theta is pi over 3, how fast does the camera have to rotate in order to keep the plane in view? So what's changing here? Well, a couple things. This is changing right here, this distance, because as the airplane approaches the photographer, this distance, we'll call it x, is getting smaller. The distance between the plane and the cameraman must be changing as well. I can call that, let's not call it y, let's call it z. All right, so what information did they give me? Well, they've given me the airplane flying at 450 kilometers per hour, and it's going in this direction. So x is going to be getting smaller, that distance from the cameraman to the plane. So dx dt is negative 450. Now, what do they want us to find? How fast is the camera rotating? In other words, they want to find out how fast this angle is changing. They want us to find d theta dt when theta is pi over 3. All right, so I need an equation that involves x and theta. What equation would involve x and theta? Well, again, I've got a right triangle here because the altitude of the plane has to make a right angle. I can't use z because I don't know enough, but I can use x and theta. Well, I know this is constant over here. What if I use the tangent function? How about the tangent of theta equals opposite over adjacent? So how about an equation tangent of theta equals 5 over x? Well, that uses all the variables I need, so let's differentiate. Derivative of tangent theta is secant squared theta times the derivative of theta with respect to t. Now 5x, we can think of that as 5x to the negative 1, so that derivative would be negative 5 x to the negative 2, or negative 5 over x squared times the derivative of x with respect to t. Now, I know theta is going to be pi over 3. I know dx dt is negative 450. I don't know x, or do I? Well, let's see here. When theta is pi over 3, then I know that the tangent of pi over 3 will have to equal opposite over adjacent, and I can solve for x. So x will be 5 divided by the tangent of pi over 3. Well, tangent of pi over 3, since the opposite side, let me just draw a quick 30, 60, 90 triangle here. So here's pi over 3, our 60-degree angle. So this would be the square root of 3. The adjacent side would be 1, and this would be 2. So tangent of pi over 3 would be radical 3. So x must be 5 over the square root of 3. So now let's finish this up. I know theta is pi over 3. Okay? So this says the secant squared of pi over 3 d theta dt equals negative 5 over the square root of 3 squared times dx dt, which is negative 450. Now, secant of pi over 3, let's back up here. Secant is hypotenuse over adjacent, so 2 over 1. So secant of pi over 3 is 2, squared is 4 times d theta dt equals negative 5 over, if I square this, I get 25 thirds times negative 450. Continuing on with this, let's see if I can give myself a little more space here. Now I have divide both sides by 4. Now you might want to clean this up first, I suppose. Negative 450 times 5, what's that, 2250? So 2250, instead of dividing by 25 thirds, I can multiply by the reciprocal, I guess, 3/25. So 25 goes into 2250, is that 90 times? And 90 times 3 is 270. Does that make sense? Let's see here. 225 divided by 25. It goes in 9. Yep, 90 times 3 equals 4 d theta dt. So finally, d theta dt would equal 270/4, which is 67.5, right? 270 divided by 4, I think. So, what's my answer? How fast does a camera rotate? Well, what is theta going to be measured in? Well, it's going to be measured, how do we measure angles? In radians, right? Pi over 3 radians. So, the camera rotates at a rate of 67.5 radians per, what's the unit of time we have here? This is kilometers per hour, so that must be radians per hour. So it's moving pretty quickly at that moment. And there you go. And we are done. Good luck with related rates.